Hello and welcome to the session on strength of material. In this session, we'll be discussing about the shear force and the bending moment diagram. I am Professor V. Khond, working in the Mechanical Engineering Department at Kekwak Institute of Engineering Education and Research, Nasik. So, start with introduction. So, we have SFD and BMD are used for the analysis of beam. SFD is basically the variation of shear force along the beam length. BMD is the variation of bending moment along the beam length. Then value of shear force is used to calculate the shear stresses. Value of bending moment is used to calculate the bending stresses. So we will be seeing the two concepts, that is shear stresses and bending stresses, in the next unit, that is the bending stress and the shear stress, that is the shear stresses in machine element. So for this particular case, this is related with the beam theory. So in the beam theory, we will be having the shear force, first concept, second concept is the bending moment. So both the concepts are used to get down the beam theory. So for getting into the details of the shear force and the bending moment diagram, let us see what are the different types of load. So first type of load is concentrated load, which is acting at a point. So load acting at a particular point, is called as concentrated load. So in this case, we are having the 2 points, one point P1, another point P2. So for load acting at a particular point is called as concentrated load. So it is a kind of beam. It is a kind of beam which is supported at the two ends. Okay. Now another kind of load is uniformly distributed load, wherein the load is uniformly distributed over the entire span of the beam. So here it is W Newton per meter. W is the magnitude having the unit Newton per meter. So Newton is the load per meter. So for 1 meter length of the span, we'll be having the magnitude W. Then uniformly varying load. So it is the load is very uniformly varying along the span given. So in this case, it is this particular span is given. So W Newton per meter. Again, there is a magnitude. So you can see over here, it is 0 magnitude over here. Here it is maximum magnitude. So maximum load will be acting over here. 0 load will be acting over here, and it is uniformly varying. Now this is another kind of load, which is the applied couple acting at this particular point. So it is applied couple is M acting at a particular point. So these are the different kinds of load. Now we'll go with the types of beam supports. Now, so these are the different. So first one is the simply supported beam. So it is a beam having two supports. One support is over here, another support over here. So this support is being called as hinge support. This support is being called as roller support. So it is a beam, simply supported beam. One at the hinge support, another one is at the roller support. Then this one is overhanging beam. So some part of the length is overhang. So that is being called as it is a type of simply supported beam, but some part portion is being overhang. Again the same thing, hinge support and the roller support. Then the next one is cantilever beam. So one end is fixed over here, another end is free over here. Then it is a continuous beam, where the beam is being supported with two or more supports. More than two supports, that is called as continuous beam. Then beam fixed at one end and simply supported at another end. So it is fixed at over here, and at the other end it is just a roller support, wherein we are having only one reaction from the downward side. But in this case, in the fixed support, we are having the x axis load, y axis load, and the moment. Then it is fixed at both the ends. So at both the ends, at this end and this end, both the ends are fixed. So at both the ends, we are having the two kinds of reactions. One is the vertical reaction, normally we take, and moment. Another reaction is moment. Then we come into the concept of the shear force. What is shear force? So it is nothing but it is an unbalanced vertical force on one side to the left or right of the section of the beam, and is the sum of all natural normal forces on one side of the section. So basically it is the unbalanced vertical force on one side of the beam. Okay. So let us talk about the sign convention for the shear force. So when you are going for the problem solving, so we have to take the sign convention for the shear force. So for that case, we are normally we take the section over here. Normally we take the section. So section, left hand side of the section, upward force positive, downward force negative. Similarly, section, right hand side of the section, upward force negative, downward force positive. So that is what the shear force. So basically shear action means a cutting action. So coming to the bending moment. So in the bending moment, it is the algebraic sum of the moment about the section of all the forces on one side of the section. So now coming to the sign convention for the bending moment, again the section we have to take section, left hand side of the section, clockwise positive, anti-clockwise negative. Section right hand side, anti-clockwise positive, clockwise negative. So if you take the this particular action both positive, so positive bending moment means it is a sagging bending moment where the if you take a beam, so beam will get bent in this particular direction. So in this action, this is the what we can say the bending action. So normally the beam will get sagged, and so that's why it is being called as sagging bending moment. So in the downward portion, so if you take the bending moment in this direction, and over here if the beam bends like this, so that is called as the hugging bending moment. So two types of bending moment, hugging bending moment and the sagging bending moment. Now we'll differentiate with the shear force and the bending moment with a simple example. So this is a simple example wherein we are having the load, or we can say it is a overhanging beam wherein we are having the two supports, one support over here, another support over here. R1 is reaction 1, R2 is the reaction 2, and the concentrated load or the point load acting at different points. So W1, W2, W3, W4, these are the loads. So if you take the case of the shear force, so shear force, for the shear force you have to take the section. If you take the section over here, x that is the section being taken, and whatever the you have to take the either left hand side or the right hand side of the section. So if you take the left hand side of the section, so all the forces W1, W2, W3 and R1, if you combine and get down the resultant, so that will be the F. So which will try to lift this particular portion of the beam in the upward direction, and this one if you take this combination of these two, so that will be in the downward direction. So the net results will be to cut the beam at the section XX. So that is what the action of shear force. Now if you take the bending moment, so if you take the section over here, so the forces, because of the forces, the beam will get sagged in this particular support between R1 and R2. So beam will get because of the forces. So one force, another force, another force. Because of these forces, the beam will get sagged like this. So that is being called as, so action is like this. That is positive bending moment. So it is a sagging bending moment. At this particular point, the beam will be like this. So in a direction will be negative. So it will be hugging bending moment. So these two types of bending moment, sagging bending moment and the hugging bending moment. Now we'll see the relation between the load SFD and the BMD. Now the load is equal to d by dx of shear force. So if you take the load W, so that will be equal to differential of shear force. So we can say slope of the shear force diagram, but we'll get the slope of the shear force diagram. So that will be equal to the applied loading. Then so shear force will be equal to differential of bending moment, d by dx of bending moment. So that will be equal to slope of moment curve is equal to shear force. Then variation of shear force under bending moment will be like this. So consider different cases, consider the type of load, consider the shear force diagram and the shear bending moment diagram. So if you take the point load, so in the shear force diagram we'll be having the horizontal line. In the bending moment diagram we'll be having the inclined line with first degree curve. So if you take the uniformly distributed load, in the shear force diagram we'll be having the inclined line with the first degree curve. In the bending moment diagram it will be parabolic curve with the second degree curve. if you take the uniformly varying load in the shear force diagram, we will be having the parabolic curve with the second degree curve, and bending moment diagram with the cubic curve, that is the third degree curve. So that is what variation of the shear force and the bending moment diagram for different kinds of load and different diagrams. I will take with the take this one example for solution. Find the SFD and BMD for the following loaded beam. So this is the beam. So this kind of beam. So this is the cantilever beam which is fixed at one end, free at another end. Okay, and the another end is not supported or not fixed. So it is cantilever beam, and support. Support is over here. Support over here. And the different kinds of load. One load is point load at point B, that is 3 kN. Another load is uniformly distributed load between C and D span, or that is 2 meter, and the magnitude is 1 kN per meter. And another concentrated load at point E, that is magnitude is 2.5 kN. Okay, so we'll try to solve this particular problem. So let us take the reactions. So reactions will be at this particular point, the reactions are A, vertical reaction, and the moment MA. So initially you have to find out the reactions first, and then go for the shear force calculation and the bending moment calculations. So for the shear, for getting down the reactions, so reaction is the total load of the span. So that is will be equal to RA will be equal to total. So we have to take the all vertical forces. So all upwards is equal to all downwards. So all downwards, that is 3, okay, plus that is 3 plus 1. So 1 multiplied by 2, because it is a uniformly distributed load and varying over the span, so distributing over the span. So 1 multiplied by 2 plus 2.5 plus 2.5. So we have to convert UDL into the point load. So to convert the UDL into point load, you have to take the magnitude and the meter on which it is being loaded. So 1 multiplied by 2, that is equal to 2. So overall we'll be having the reactions will be equal to 7.5 kN. So all downwards is equal to all upwards. So upward is only one force, that is RA, that is only the reaction. Now for the moment, so for the moment you have to find out the moment. So moment at point A. So moment, for getting the moment at point A will be equal to, you have to apply the engineering mechanics principles. So 2.5 into this particular distance, that is 5 minus 1 multiplied by 2, converting into point load multiplied by center. So 1 plus 1.5 plus 1, so that is will be equal to 3.5 distance, because it is acting at this particular center. So 1 plus 1.5 plus 1, so that will be equal to 3.5 minus 3 into 1, so that is coming as 22.5. So this is the reaction and this is the moment. So we have to satisfy these two conditions for whenever we are solving the problem. So coming to the shear force calculation, so this is what the shear force diagram will be getting. I will just check the shear force calculation. So shear force at point A, shear force at point A, shear force at point A, just left. So if you take the point A, so just left, so there is no force, just left, left of left, there is no force, so it will be equal to 0 Newton. Then just right of A, just right of A, so shear force will be equal to reaction. Okay, it will be the reactions at this particular point. So that is 7.5. Okay, that will be 7.5. Then at B, just left. B, just left, there will be only reactions at A. So 7.5. After B, that is just right of the B. So 7.5 minus 3. So that will be equal to 4.5 kilonewton. Then next is shear force at point C. Again the same thing, 7.5 minus 3, that is equal to 4.5, because there is no force prior to this. Okay, then so after C, again the same thing we will be getting, but at D point, so this force will be added, this uniformly distributed load will be added. So 4.5 value the same will be remaining same, minus this magnitude 1 multiplied by 2, that will be coming as 2.5. So 4.5 minus 2, that will be coming as 2.5. So at D. Now at E, so 2.5 at E, just left will be 2.5. Okay. So at E, just right of E. So 2.5 minus 2.5, because there will be 2.5. So it will be equal to 0. So 0. So that is being satisfied. So for getting the shear force diagram, so all the value. So say 7.5, mark 7.5, 7.5, 4.5. So just put down at the point B 7.5 and 4.5. At B there will be two values, so 7.5 and 4.5. Then at C, so it will remain constant, magnitude will remain constant, 4.5. Then 4.5 to 2.5, because it is a uniformly distributed load. So according to our variation in the diagram, so if the load is uniformly distributed load, in the shear force diagram it will be inclined line. So that is the thing we have taken. So 4.5 and 2.5, then it will remain constant. Okay, because it is what concentrated, for the concentrated load, the uniform shear force diagram will be horizontal. Okay. So that is what we have taken and drawn the shear force diagram. And bending moment diagram. So for the bending moment diagram, this is the what we are having, the bending moment diagram will be getting. So we'll just check the values, bending moment calculations. Okay. So bending moment at free end, that will be equal to 0. So this is the free end, that will be value will be equal to 0. Then next, bending moment at point E. Bending moment at point E, again it is 0, because it is a free end, so value will be equal to 0. Then bending moment at D. So to take the bending moment at D, so we'll consider right hand section. If you consider right hand section, downward force, and it is going into clockwise direction, so the clockwise negative section, right hand side clockwise negative, so minus 2.5 multiplied by 0.5, that will be equal to minus 1.25. Now at point C, so we have to consider two forces. So one force is 2.5, another one is uniformly distributed. So minus 2.5 and distance, force into distance. So this is the force, and we have to consider distance. So at section taking the section at C, so section right hand side 2.5 multiplied by 2.5 minus 1 multiplied by 2, converting to point load, and the distance is 1, because center is the distance, so it is acting at this center. So 1 multiplied by 2, point load multiplied by distance 1. Okay, so that will be coming as minus 8.25. Then bending moment at point B. So we have to consider three forces. One is 2.5, another one is 1. So again but distance varies. We have to consider the same forces, but the distance varies, because at B the distance varies. So it will be equal to minus 2.5 multiplied by 4. So 1.5 plus 0.5 plus 2, that will be 4, minus 1 multiplied by 2 multiplied by 2.5. So that will be coming as minus 15 kilonewton meter. Then bending moment at point A. So all the forces being taken, distance varies, minus 2.5 into 5, minus 1 into 2 into 3.5, minus 3 into 1. So that will be coming as 22.5. So our reaction at point A is also equal to 22.5. So it is being matching. So it means whatever the values we got, it is correct. So draw the diagram. So all it is actually, it should be minus, it should be equal to negative over here. So whenever it is negative, so from the horizontal line you have to plot in the downward direction, because it is minus. So minus 20.5, minus 15, minus 8.25, and here it is a parabolic curve, because it is uniformly distributed load. So whenever convention is that whenever it is uniformly distributed load, so in the shear force diagram it will be inclined line, and in the bending moment diagram the curve will be parabolic curve. Okay, from D to E, again the inclined line, again the inclined line, because the load varies over here. The load varies because you have to take the convention again, the same again the convention point load in the loading diagram. Whenever it is point load in the loading diagram, in the shear force diagram it is horizontal line, and in the bending moment diagram it is the inclined line. So that convention you have to follow, and you'll be getting the diagram like this. Okay. So this is the reference. I have taken the reference from the study material for some, that is from the STS College Pune and the book by S.S. Ratan. So thank you for listening. If you like this video, then like it. Also, please subscribe my YouTube channel by pressing the bell icon button and never miss the updates. So thank you for